Hey everybody, this is a few problems on Coulomb's law, just pretty basic, straightforward problems. If we remember, Coulomb's law tells us that the force between two charges is equal to the Coulomb constant times the first charge times the second charge over the distance between their center of charge squared, where K is a constant, 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. And we also know the charge on an electron, or proton, is 1.60 times 10 to the minus 19 coulombs. We'll use those two to solve these problems. Okay, so problem 1. A particle of mass 80 grams and charge 12 microcoulombs is released from rest when it is 41 centimeters from a second particle of charge negative 16 microcoulombs. Find the magnitude and nature, attractive or repulsive, of the electrostatic force on the 80-gram particle and the magnitude of the initial acceleration of the 80-gram particle. So let's get started. Since we're solving for, well, actually first of all, we have our two charges. We know that one of them is our 80-gram charge, Q1, is equal to 12 microcoulombs. Q2, the other charge, is equal to minus 16 microcoulombs. So right off the bat, they're opposite charges. We know it's going to be an attractive force. And it says that they're 41 centimeters apart, so my distance r is equal to 41 centimeters, or in meters, 0.41 meters. And that's all I need to find the force. F equals K Q1 Q2 over r squared. So that's equal to 8.99 times 10 to the 9 times 12 microcoulombs, that's 12 times 10 to the minus 6, times negative 16 microcoulombs, negative 16 times 10 to the minus 6, divided by our distance squared, and our distance is 0.41 meters. Keep it in base SI units, and we square that whole thing to get our answer. The force between our charges is, plug it into a calculator, make sure you put the denominator in parentheses and square it. We get a force of negative 10.3 newtons. And that negative sign just tells us that it's an attractive force. Whenever we have opposite charges in our Coulomb's law, Q1 and Q2 are opposite signs, it'll give us a negative answer. If they're like charges, we'll get a positive answer. But we already identified that as attractive. Part B, find the initial acceleration of the 80-gram particle. Well, we know F equals ma. So A equals F over m. Our net force is 10.3 newtons, and the mass is, it's 80 grams, so 0.08 kilograms. Plug that into a calculator. Our answer over 0.08 equals 128 meters per second squared. Is our initial acceleration. That's the magnitude. And it's going to be accelerating towards the other charge because it's an attractive force. Next question. Two charges, big Q and little q, are at a distance from each other, at a distance d from each other, and experience a force big F. Find the new force F prime in terms of F if the following changes are made. A, the distance is tripled. Whoops. That should be, so that means d prime is equal to 3d. B, both charges' magnitudes are cut in half. C, both charges' magnitudes and the distance between the charges are doubled. Okay, let's think about A. Well, for all of these, we're going to use Coulomb's law. And we know that the force is equal to KQQ over r squared, but K is always a constant, so it's proportional to Q1, Q2 over r squared. But everything's constant here except for, well, in A, just the distance is tripled. We know that if we triple the distance, keep everything else constant, since our force is proportional to 1 over r squared. Multiplying r times 3 implies that the force is multiplied by 1 over 3 squared, which means our force is going to be multiplied by 1/9. So F prime equals F over 9. We can use that same proportional reasoning for part B. Both charges' magnitudes are cut in half. So we know that the force is proportional to Q1 Q2 over R squared. But in this case, the distances are constant. We're just changing the force, so it's proportional to Q1 times Q2, or big Q times little q. So multiplying Q1 times 2 and Q2, whoops, not times 2, we're making them smaller, Q1 over 2 and Q2 over 2 implies that the force is multiplied by 1 over, whoops, a lot of mistakes here, but that's okay, we correct them fast. Since Q1 and Q2 are in the numerator, it's times 1/2 for the first charge and times 1/2 for the second charge, which means our force overall is multiplied by 1/4. So F prime equals F over 4. Part C. We double both the magnitudes of the charges and the distance, so this we're going to use everything. Force is proportional to Q1 Q2 over R squared. We multiply Q1 times 2, Q2 times 2, and R times 2. That implies force is going to be multiplied by 2 for Q1, 2 for Q2, and 2 divided by 2 squared, 4 over R squared, which gives us 4 over 4, gives us just 1, force times 1, so F prime equals F. If we double all three quantities, our force stays the same. Next question. Two conducting spheres are charged up so that there is an equivalent net charge on each sphere. When they are placed 18.0 centimeters away from each other, the force between them is measured to be 16.0 newtons. Find the charge on each sphere. So we're given that the distance, which is R, is 18.0 centimeters. We're given the force is 16.0 newtons. We want to find the charge on each sphere. Q1 is unknown, and Q2 is unknown. But we also know that Q1 equals Q2. So I'm just going to call them Q. Now let's set up our equation. F equals K Q1 Q2 over R squared. But since Q1 and Q2 are the same, we can write that as F equals K Q squared over R squared. And we want to solve that for Q, the charge. So I'm going to multiply both sides by R squared and divide both sides by K times R squared divided by K. R squared cancels, K cancels. We're left with Q squared equals R squared F over K. Now to solve for Q, we just take the square root of both sides. That cancels out the square. We're left with our final answer, or solution. Q equals root of R squared F over K. Plug in our numbers, we get R is 18.0 centimeters. We need to write it in meters, so 0.18 meters, and that's squared, times the force, which is 16 newtons, over Coulomb constant, 8.99 times 10 to the 9. Plug that into a calculator to get our value for each of the charges. 0.18 squared times 16 over 8.99 times 10 to the 9. Make sure I put my denominator in parentheses and take the square root of that. I get 7.59 times 10 to the minus 6, and the units are coulombs. I could also write that as 7.59 microcoulombs. That's that. Hope it was helpful. Bye.